Hello, good day everyone. This is Dominic Manuel. At this lesson, we will tackle the rational function, specifically in finding asymptotes, domain, intercept, and graphing of the rational function. Let's explore. Rational function. Briefly describe or discuss what is a rational function. A rational function is a function of the form r of x is equal to p of x all over q of x, where p and q are polynomial function and q is not the zero polynomial. The domain of R is the set of all real numbers except those for which the denominator q is 0. So here's some of the tips to work on the rational function. So whenever you're working with the rational function, always remember to identify and exclude the values that make the denominator 0 to ensure the function is properly defined. So therefore, you don't need the denominator to be 0. So that's the golden rule. So let's first touch in the domain. So the domain of a rational function is found using only the vertical asymptote. As previously noted, rational functions are undefined at vertical asymptotes. The rational function will be defined at all other x values of the domain. So in other words, domain is determined by identifying the vertical asymptotes which occur where the denominator is 0. The function is undefined at this asymptote but is defined for all other x values in the domain. So later we will solve an example for the domain of the rational function. Let's have an example on how to find the domain. So say for example, f of x is equals to x over x plus 3 and x minus 5. So this is the rational function in complete factored form. So we all know that the domain refers to the zeros of denominator. So what are the denominator? X plus 3 and x minus 5. Very good. So we're gonna zero it. So x plus 3 equals to 0. And x, we're gonna transpose 3 across the equal sign. So therefore, it is negative 3 as well as the x minus 5. Transpose equals to positive 5. So here are the domains. X minus 3 and x equals to 5. For our domain is x such that x is an element of real number such that x is not equal to negative 3 and x is not equal to 5. Why? Because the reason for excluding negative 3 and 5 from the domain is that these values from the denominator becomes 0, making the entire function x over x plus 3 and x minus 5 is undefined. So here are the clarification. If f of x is equals to x over x plus 3 and x minus 5, so if we substitute this function into negative 3, so the values becomes like this: 3 minus 5, negative 3. Okay, so negative 3, so negative 3 plus 3 is 0 and negative 3 minus 5 is negative 8. So if we multiply this, it will become negative 3 over 0 that answer and undefined. It is undefined because your denominator equate to 0 and that's not a real number. As well as the 5, if we equate 5, so 5 over 5 plus 3 and then 5 minus 5 equals to 5 over 8 and 0. Why? Because 5 plus 3 equals to 8 and 5 minus 5 equals to 0. Multiply this 5, 0 to become undefined also. Because the denominator becomes 0. So this is the graph of the domain. Notice that the graph didn't touch the negative 3 and positive 5 because we all know that the x is not equal to negative 3 and x is not equal to negative 5. Example number 2. Find the domain of f of x equals to 1 over x, and let's discuss the behavior near any excluded x values. So the solution of this is the domain of f is all real numbers except x equals to 0 because our domain is x equals to 0. To determine the behavior of f near this x value, evaluate f of x to the left and to the right of x equals to 0. So when x approaches 0 from the left, so it will become negative. So if we equate, if we put negative 1, our f of x also negative 1 because 1 over negative 1 is negative 1. If 0 negative 0.5, our f of x becomes negative 2. And so on and so forth, it will become 0 to negative infinity. On the other hand, if f of x or x approaches 0 from the right, if we put 1 in the x, so 1 over 1 equals to 1. And then as well, if we put 1 over 0.5, it equals to 2. And we put 0.1, it equals to 10, so on and so forth, that the function will become 0 to positive infinity. So this is the graph of the function equals to 1 over x. Notice that in the x approaches to left, it didn't touch from the 0. And x approaches to right, didn't touch 0. Okay, now we're done determining the domain of the rational function. Now, we'll need to find the asymptotes. So, rational functions have various asymptotes. The following will aid in finding all the asymptotes of a rational function. The first step to working with the rational function is to completely factor the polynomials. I repeat, completely factor the polynomials. Once in factored form, find all zeros. Example number 3, to find the vertical and horizontal asymptotes. So we have function 2 over x minus 1 squared. So that's a completely factored form. So now let's find the vertical asymptote first. So we all know that the vertical asymptote relies on the denominator. So therefore x minus 1 equals to 0. So x equals to 1 because the 1 will be transposed across the equal sign. So therefore our vertical is x equals to 1. Now on the denominator, since an x value of 1 or would create 0 in the denominator, so the function would be undefined at that location. As a result, this is our vertical asymptote for this function. In this same function, the degree of the numerator is less than the degree of the denominator. Therefore, the horizontal asymptote is y equals to 0. So this was discussed in the guidelines earlier. So the y equals to 0 because the numerator is less than compared to the denominator. Okay, let's have an example of finding the asymptote. So suppose that or assume that our function is f of x equals to 2x plus 1 and over x plus 1. So this is the complete factored form. So we'll find the vertical asymptote first. So remember, the vertical asymptote relies on the denominator. So x plus 1 equals to 0. So our vertical asymptote is equal to negative 1. Just remember that if you transpose the value of the denominator across the equal sign, it will become negative. If your values is negative and you transpose it across the equal sign, it will become positive. So that is the vertical asymptote. So on the other hand, if you find the horizontal asymptote, you need to determine the degree of the numerator and the degree of the denominator. So let's say for example 2x plus 1 2x plus 1 and x all over x plus 1. So the degree of the numerator is the highest degree of the numerator is x as well as the denominator. So what could be the possible reason for that? So we all know that there are guidelines of the horizontal asymptote. So if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the two leading coefficients. So let's find the ratio of the two leading coefficients. So since there are sa function numerator is the leading is x and also the denominator is x, so therefore they are the same. So let's determine the leading coefficient. Since the leading coefficient of the numerator is 2, so this is the leading coefficient over the x. This is the leading coefficient of the denominator. So if we equate this, y equals to leading coefficient numerator over leading coefficient denominator is equal to the leading coefficient of the numerator is 2 over the leading coefficient of the denominator is x, and x is equatable to 1. So therefore 2 over 1 equals to 2. So therefore the horizontal asymptote is y equals to 2. Let's have an example of finding the oblique asymptote. So, suppose that f of x, we have f of x is equal to x squared plus 8x minus 20 over x minus 1. So first thing to do is divide the leading term of the numerator by the leading term of the denominator. So since the leading term of the numerator is x squared, you need to divide the leading term on the denominator, which is x, which equals to x squared divided by x is equals to x. So here's step 1. Step 2 is multiply the entire denominator by this result. So therefore, x times x minus 1 is equals to x squared minus x, because x times x and x minus 1. So this is the process number 2. Process number 3 will be subtract this from the original numerator. So therefore, you need to subtract this x squared plus 8x minus 20 minus x squared minus x, which will become x squared plus 8x minus 20. Transpose the operation, so the x squared will become negative x squared, and the negative x will become positive, because negative times negative is equal to positive. That's good. Negative x squared plus x. So eliminate the opposite term. So positive x squared cancel to the negative x squared, and then 8x, the like terms will be added. So 8x plus x equals to 9x, and then copy the negative 20 because it's just the only one. So this is the equation 3, 9x minus 20. And then let's proceed to equation number 4. Repeat the process with the new polynomial. So let's just repeat. So the leading term is 9x over x, because the leading term, the denominator, is x. So equals to 9, because 9x over x is equals to 9. And then multiply again the denominator. 9 times x minus 1 equals to 9x minus 1. It's the equation 5. And then subtract again. So therefore, there is 9x minus 20 minus 9x minus 9. This is 9 pala. So we subtract the 9x minus 9 to the new equation, new polynomial. So 9x minus 20 minus 9x plus 9 is equals to, cancel the 9x. So therefore, and subtract, therefore we get negative 11. So in summary, we find the division f of x is equals to x plus 9 plus negative 11 over x minus 1. And then the oblique asymptote is given by the linear division, which is y equals to x plus 9. In summary, oblique asymptote, the function is y equals x plus 9. So since we have tackled the different types of asymptote, now let's proceed on finding the intercepts. So we have found that the zeros of the denominator of a rational function are the vertical asymptotes of the function. The zeros of the numerator, on the other hand, are the x-intercepts of the function. So let's try to find, or let's have an example of finding the intercept. So assume that f of x is equals to x squared minus 16 over x minus 3. So finding the x and y intercept. So in x-intercepts, what we're going to do here is we need to rely on the numerator since that's the process of the x-intercept. So what is our numerator? X squared minus 16. Is x squared minus 16 is factorable? Yes, it is factorable. So to find the x-intercept, we need to factor the numerator, which is the factor of the numerator. X is x plus 4 and x minus 4 over x minus 3. So we write out the function in completely factored form. So we need to find the zeros of the numerator. So x plus 4 equals to 0, and then x equals to negative 4. X minus 4 equals to 0, so x equals to 4. So these are the x-intercept of the function. This is the x-intercept. Try to find the y-intercept. So the y-intercept is, we need to substitute 0 for x and find the y-intercept, which in this case will be the ratio of the two constants. So therefore f of x is equals to 0. So f of 0 is equals to x squared minus 16 over x minus 3. So 0 is equals to 0 squared minus 16 over 0 minus 3. Then f of 0 is equals to 0 times 0 equals to 0 minus 16, copy, and then 0 minus 3. And f of 0 equals to 0 minus 16 equals negative 16, and 0 minus 3 equals negative 3. So therefore, if we simplify this, negative divided by negative is positive. So therefore, our y-intercept is 16 over 3, because the 16 over 3 is not simplifiable. And then the y-intercept is equals to 16 over 3. And that's how to find the x and the y-intercept. The golden rule is from x-intercept is write the factored form of the numerator and find the zeros of the numerator, and then the y-intercept is substitute x for 0 to find the y-intercept. Okay, so since we're done tackling about the finding the intercept, so now we'll proceed to graphing of a rational function. So there are guidelines for graphing the rational function where and are polynomials with no common factors. So there are 7 steps to graph a rational function. Number 1, find a plot the intercept, if any, by evaluating. Number 2, find the zeros of the numerator, if there's any, by solving the equation, then plot the corresponding intercept. Number 3, find the zeros of the denominator. So therefore, if we said denominator, so it's a vertical asymptote. Number 4, find and sketch the horizontal asymptote by using the rule for finding the horizontal asymptote of a rational function. Number 5, test for symmetry. Number 6, plot at least both between and beyond each intercept and vertical asymptote. And lastly, use smooth curves to complete the graph between and beyond the vertical asymptote. So there are various examples I want to show you on how to graph a rational function. Let's sketch the graph of the rational function. So suppose we have x over x squared minus negative x and negative 2. So what we're going to do is to find the y-intercept, the x-intercept, the vertical asymptote, the horizontal asymptote, and the x and y, or the graph. So let's find first the y-intercept. So we all know that the y-intercept is f of x is equal to 0, f of 0 is equals to x over x squared minus x minus 2. So f of 0 is equals to 0 over 0 squared minus 0 minus 2. So f of 0 is equals to 0 over negative 2. Therefore, our y-intercept is equal to 0. Now let's find the x-intercept. X-intercept. So we all know that x-intercept relies on the numerator. So our numerator is x. So therefore, our x is equals to 0. So the x-intercept is 0, 0. The y-intercept also is 0, 0. Now we have to find the vertical asymptote. So the vertical asymptote relies on the denominator. So does our denominator is factorable? Yes, it is factorable by vertical asymptote. So x squared minus x negative 2 is factorable by x plus 1 and x minus 2. So therefore, our vertical asymptote is x plus 1 equals to 0, x equals to negative 1, x minus 2 equals to 0, so x equals to 2. So our vertical asymptote is x equals to negative 1 and x equals to 2. So let's find also the horizontal asymptote. So we all know that there are guidelines since the degree of p of x, which is the numerator, is less than the degree of the q of x, which is the denominator. Therefore, our horizontal is 0, or y equals to 0. Let's make a table for it. So if we put negative 3 on the x, if the answer will be like this. So we substitute negative 3. So negative 3, negative 3, negative 3 over negative 3 plus 1 is negative 2, negative 3 minus negative 2 is negative 5. So it's equals to negative 3 over 10, or f of x is equals to negative 0, negative 0.3. This. And then if we input negative 1, it will be undefined because our vertical asymptote is x is equals to negative 1 and x equals to 2. So therefore, it is not, if we input negative 1 and the value, it will cost an undefined. So same process on negative 0.5, same process like the negative 3, and it will be come up to 0.4. And if we put 1, the answer will be negative 0.5, same process, and 2 is undefined. Undefined because another vertical asymptote where x equals to 2, the zeros of the denominator. If we input 3, it will be 0.75. So if we graph it, this is the graph of the function x over x squared minus x negative 2. So our first vertical asymptote, which is x equals to 2, right here, you put broken lines in the vertical asymptote, and the second vertical asymptote is x equals to negative 1. So so the purpose of asymptote is the guide for your graph on the table of values. Like, say for example, you have negative 3 and 0.3. So the graph should not touch the vertical asymptote. So the motion of your graph is like this, and the value on that value. And then we all know that our horizontal asymptote is y equals to 0. That's why it's in the center. And then another value is negative 0.5 and 0.4. So here. And then 1 and 0.4 here. That's why the graph should be like this. It hindi dapat mag-touch sa vertical asymptote. The last graph is the 3, which is here. 3 and 0.75. So it will not touch in the vertical asymptote, which x equals to 2. So that's the proper graphing of a rational function. Okay, since we covered all the lessons in the rational function, so let's have a problem exercise. So in letter A, 1 to 5, find all the asymptote, intercept, and the domain of the following function, but do not graph this function. In letter B, you just only need to identify the vertical asymptote and the horizontal asymptote of each item, but you need to sketch the graph. Well done! You should now have a solid grasp of finding the domain, intercept, and the asymptote of rational functions, and how to sketch their graphs. This knowledge builds essential skills for tackling math problems and prepare you for more advanced studies. Keep practicing, stay curious, and explore the fascinating patterns in mathematics. Great job, and keep it up!